Okay, we have a great meetup today. We got some great speakers, and we've got a startup. Actually, we have, I guess, two startups. Baseten has been around a little bit longer, but they are doing awesome stuff. So we have Philip Kiely. He and I go back quite a bit. Well, probably maybe earlier this year is when I finally connected with him. One thing about Base 10 is I've I come across their blog posts all the time, and I kept seeing the same names over and over, and it was Philip and his team. And so I, reached out to Philip and said, "Hey, man, just want to let you know your blog posts really mean a lot to me. I've learned quite a lot." He talks a lot about arithmetic intensity and all the cool performance things that I needed in my previous roles, as well as for the book that I'm writing, which is this AI system performance engineering. Quick update on this, by the way, it's in the final editing. In fact, I have to get back to the O'Reilly folks this week about some edits, and then moves right into production. And I'm hoping for an October release. Unfortunately, these things take time with the high quality standards of O'Reilly. So yeah, Philip, awesome stuff. He's going to give us a talk today, I believe, on TTS and text to speech and voice agents, and really about inference and low latency inference, which is what this meetup is all about, is high performance. Second talk's going to be from Emilio Andere, and he's from a startup, actually Y Combinator startup called Herdora. And he's working on tools that can profile and actually help to optimize your PyTorch kernels, CUDA kernels, any kind of code that you have. So again, right in line with exactly the thesis for this meetup. And then I actually have a surprise, and I haven't even showed the like Herdora folks this yet, so they'll see it today for the first time. But I've also been working on something kind of similar, and so I want to demo it to him and to the team and to this community to show a tool that can also take PyTorch code as well as CUDA code, although I think that part's broken right now. So I think I'm just going to focus on the PyTorch code. I was fixing it this weekend and broke it, of course. And you then upload your PyTorch code. It'll actually create different variants. It'll test them out. It'll compare them, show a leaderboard, and you can take further action to dive in and really understand the optimizations that are happening. And so, as like the other thesis for this meetup is really teaching folks about these concepts. And so I think all of these topics fit really well into it. And I think quick reminder, next month, we've got a talk from NVIDIA, and I'm trying to get the VLLM folks on here as well too, to dive deep into KV caches and some of the internals of VLLM. Subsequently, I'm hoping to get some of the folks from the SG Lang community, which is another inference engine, kind of similar to VLLM, at least in concept. And yeah, just continuing to find the right folks to bridge this gap of understanding about performance in modern AI and LLM servers. So with that, all the links are here in the meetup. And Philip, you're going to talk first. You talk as long as you want, although I guess out of respect for Emilio, maybe give him 20 minutes or so towards the end, and then I'll flex to whatever you folks end up doing. I'll talk over the hour and just get it recorded and then posted. So all of this will be posted. We'll post the links throughout. And Philip, are you ready?
I'm ready. So, hello everyone. I'm Philip. I'm going to go ahead and share and get some slides up. Let's see, just need to have the current share switch off, and then we'll be able to get started. I'm going to speak pretty briefly, I think, about a few topics just to give people a sense of the kind of things that I've been working on and learning about, and then ideally we've got 150 people here, which is amazing on a Monday morning. Thank you all so much for being here, by the way. And what we're going to do is I'm going to give a quick talk through a few different ideas, and then we're going to go into some questions and answers. So this is just a quick little preview, and then whatever you're interested in learning more about, we can do some deep dives there. So listicle title, 3 things to know about AI infrastructure as you scale. Quick introduction. I'm Philip. This is me with a bunch of my friends at Base 10. and we work on AI infrastructure. So what we've been able to see sort of up close and personal is the challenges of serving models with very, very low latency for real-time applications at the sort of scale that some of these leading AI native companies are hitting. So today I'm going to talk about three things, two kind of trends that have been observed recently in the market, and then three quick little case studies around some technical wins that we've been a part of. And from there, we're going to be able to look at some patterns across all of these and what makes it hard to do this sort of stuff in production. So trend number one, AI natives. What is an AI native company? So there's this, new class of companies, I think best exemplified by Koso, but there's, hundreds of them at this point that are scaling really fast. AI native startups are scaling toward $100 million ARR at an absolutely record pace, and they're scaling with fewer employees than ever before. And the reason this matters from sort of an engineering perspective is that you start to think about, growing this fast with this small of a team, and things that maybe in the past would have been considered premature optimization or over engineering are actually the right thing to do. Because if you're going to be, doubling your user base month over month over and over again, you're going to run into some of these scaling challenges very, very quickly. And it's worth, building ahead of that a little bit in a way that maybe wasn't worth that investment in the past. So here are some examples of like AI native companies, some of the ones that I've been fortunate enough to work with here at Baseten. So some great examples of like what an AI native product looks like is something like Open Evidence, which is basically ChatGPT for doctors, where, if you think about ChatGPT, it's got to be fast and reliable. And if it's ChatGPT for doctors, it's got to be even faster, even more reliable. Or you have something like Zed. Zed's this really cool product. I think, with this being a performance-oriented meetup, they're a great one to talk about because they basically are a text editor. They're an AI powered text editor, just like Koso or something. But what's cool about Zed is they wrote their entire editor in Rust. So it's very performant and it's very low impact on your system. So anyway, all of these companies, what do they care about? They really care about four things in their models. They care about number one, quality, especially task-specific quality. Number two, latency for real-time use cases. Number three, economics at scale. Believe it or not, we are actually starting to try to make money here in the AI industry and not just set piles of VC cash on fire. So unit economics are starting to matter. And then finally, the most important one is differentiation, control of destiny, being able to use models and use your AI stack as a genuine differentiator in the market. So the second trend that's kind of supporting a lot of this is, and I'm just grabbing the chat open here real quick. The second trend that is supporting all this is open models, the rise of open source models. So today, I actually just updated the screenshot this morning because it's changing so fast. We're close to 2 million open source models on Hugging Face. So the vast majority of AI engineering is centered around like three models, which is GPT, Claude, and Gemini. But there's like 2 million more models out there across all different domains, all different modalities to know about. So some big ones, some big names in open source that are kind of state of the art at this point are, on the LLM side, these are the most well known. You have stuff like Kimi, DeepSeek, Llama, Qwen, GLM, of course, OpenAI's new GPT model. But what's really exciting about open models is that you have state-of-the-art models across a lot of other modalities besides LLMs. So with Qwen Image just launched a couple weeks ago. That's a fantastic new image model that rivals a lot of the Imagen models and the GPT image model. You have new like world models is sort of the hot topic of this month, and Tencent Hunyan launched their first world model, which is really exciting to have that completely open source, along with Alibaba's other lab, WAN did WAN 2.2 for video. Embedding models are a great source of open source, a great category of open source models with, again, that Alibaba Quen team shipping a lot here, along with other, startups like Nomic and Mixspread delivering great models. Transcription's basically been a solved problem for 3 years with Whisper. And then one model that I've been seeing a lot recently is Orpheus TTS over the last few months. This is an open source speech synthesis model for building with voice that is built on a Llama backbone, as we'll talk about, and it's really been delivering a lot of state-of-the-art quality at very low cost. So what's cool about these open models is that they're all these foundation models that can be iteratively built on top of. So Orpheus TTS, as an example, has that Llama 3.2 3B backbone. So even though it's a text-to-speech model, it's not an LLM. It still uses the same LLM architecture. Because of that, it still uses all the same LLM performance. You can still use all the same LLM performance tooling for it. But what's really exciting about this open model space is it lets you stand on the shoulders of giants and iteratively build more and more open models. But the challenge now that everyone's, building on these open source models is where before you just had to grab an API key and get going, now you have to scale up inference and do so quickly and cost efficiently. So why is that a problem? The issue is that the sort of standard path of, okay, I get some GPUs, I get VLM, and I don't want to pick on VLM because VLM is actually a very good technology. You could make this slide with SGLang or TRT or any framework off the shelf. Just sticking that on a GPU is not going to get you into production. And the reason for that is because of these four things that that AI native companies care about: the model quality, the model latency, the model economics, and the model differentiation. So on the quality side, well, we have these excellent open source models. In many cases, closed source models still are going to win at general benchmarks. But task-specific quality is a big differentiator for product. So what we're seeing is a number of companies building out, these task-specific models, either via fine-tuning or training their own foundation models from scratch. A great example is healthcare document processing, where, ordinary, even GPT-5 does not do a great job of like health code categorization, but a very small custom trained model can serve that task with very, very high accuracy. Again, the next thing that they care about is latency. So an example of this is like in the TTS and voice space, being able to answer every phone call with a voice agent. You see a lot of companies building on that today. I think Bland is a great example here. Where off-the-shelf endpoints are generally optimized for system throughput, you need to build latency optimized endpoints instead if you're going to be serving any kind of voice use case. The third thing, economics. So the great thing about serving your own models is that you go from being a price taker to a price maker, where you are setting your own unit economics. And the cool thing is that the trade-off is basically with anytime you can increase throughput, now that can hurt your latency a little bit. You have to find that balance. Anytime you increase throughput, you save cost, as long as you're serving high enough traffic that you're saturating your hardware. And then, of course, the final thing is differentiation. Every company is now an AI company. They don't want to outsource ownership of AI strategy, including infrastructure. And that is, that infrastructure becomes differentiated alpha. So here are three like more tangible stories of this sort of stuff in action that can provide some examples of the kind of work that goes into making this possible. So the first thing I want to talk about is instant autocomplete. Maybe drop in the chat how fast you can type. I know programmers type pretty fast, so this is a good chance to show off. I'm not the world's fastest typer. I can maybe do 60 words per minute peak, but if you wow, I'm seeing like 120 to 150. That's really impressive. So if you think about someone typing 120 words per minute and doing that as a software engineer, they're not going to want to wait around for a autocomplete or a tab complete. Even if you're like me and you're only typing at 60 words per minute, you're not necessarily going to want to pause that typing cycle to wait for an AI suggestion. It has to be instant. So we were working with this is something that SourceGraph published. SourceGraph is another wonderful AI coding tool. And what SourceGraph has is a feature called AMP Tab. Basically, it's a tab complete model that they integrated into their developer environment. Um, so obviously, if you think about the sequence of typing, and if you want to do tab complete, but it takes 700 milliseconds to be able to fill in the rest of your line of code, you might as well just type it yourself. But SourceGraph came to us. They worked with our performance team. I'll talk about what they did in the next slide, and we're able to roll out an optimization that got those latencies to as low as a couple hundred milliseconds, which is about the human reaction time. So yeah, when you're doing any kind of latency based work, by the way, like 200 milliseconds is a great rule of thumb, as that's basically a person's reaction time on average. So if you can get something to about 200 milliseconds, it feels instant. So how do we get there? We did a few things with them. The biggest thing that we did was switching to TensorRT LLM as the inference engine and using that to implement KV caching. So if you think about code completion, that's going to be something that's mostly prefill oriented. So you want to process the input sequence very quickly, and code is going to be mostly repeated. Like your code base is the same on every input sequence as you're typing on the same file. So if you have KV caching, then you can reuse a lot of those calculations and skip most of that prefill step on the sort of character to character inference basis. The other thing on the decode side is we did speculative decoding. So speculative decoding doesn't help with that time to first token, but it helps with end-to-end latency because it increases your tokens per second. We were able to use look-ahead decoding, which is one of our more commonly used speculative decoding algorithms. Speculative decoding at this point refers to a collection of like 8 to 10 different algorithms that you can choose between. And the biggest the biggest sort of fix that we made to the algorithm to make it work better was being able to support speculations of variable lengths. So rather than always doing, say, the next 3 tokens or the next 4 tokens, being able to vary that. That was, meant that we spent less compute per iteration when we needed to do a, shorter speculation, and also increased the draft token acceptance rate because we weren't speculating like multiple throwaway tokens at the end. So that's an example of the sort of model performance work that you have to do to get those state-of-the-art speeds. But there's more to it than just per GPU performance. There's also being able to scale that speed to a massive audience. So we had a customer come to us, say like, hey, we're doing a big launch. How many GPUs do you have? And what you want to be able to say to something like this is, well, how many GPUs do you need? This is a chart of this actual launch that's peaked at over 1,800 H100 GPUs. And so, yeah, coming through to this, you can see a mix of different, each one of these different colors is a different region within various cloud providers. And the way you're able to do that is by having a centralized control plane and then routing traffic to multiple workload planes, sending the traffic directly to the workload plane rather than through that central control plane. With that sort of multi-cluster model system and multi-cloud model system, you're able to support all of these requests simultaneously and scale beyond the allocation that you might have in individual clouds or regions. Finally, while you can do all of this really cool performance work, there's also invisible bottlenecks in a lot of this stuff where maybe you do all of this really cool ML and AI specific performance work, but your code is still slow. And it turns out sometimes that just comes down to good old fashioned software engineering basics. You know, I've heard a few times people tell me like, "Hey Philip, your blog post says that I can do this in 200 milliseconds. I'm running it myself. I'm getting 300 milliseconds even though I did it exactly the same. So like, are you lying about your metrics or what's up?" It turns out that like a lot of times, some of the last couple hundred milliseconds of latency that you have to get out of your system ends up being in the client code, rather than in the GPU or in the server side itself. Big one is session reuse. We hit this one all the time, where if you're not reusing your sessions, you're paying an extra 50 milliseconds of latency every time for no reason. Um, and then there's also oftentimes an issue of client throughput being the bottleneck. If you're, for example, running a Python client and doing a lot of simultaneous embeddings, your global interpreter lock is probably going to be limiting parallelism. So one thing that we created here is a performance client, especially for embeddings and for a few other types of model inference, where it's a Rust-based client that ends up being up to 12 times faster for very, very high throughput workloads because it's able to get you around those bottlenecks. So yeah, these are a handful of a quick tour of the sort of problems that you have to solve in order to hit those goals of quality, of latency, of positive unit economics, and of differentiation in this like very, very competitive market. I'd be happy to talk in more detail about any of these topics, either if we have time on this stream or if you want to reach out to me over Twitter, over LinkedIn. I'm always happy to talk about this stuff.
Oh, cool. What are like so the decision to go so one of the things I've always heard about tensor RT LLM, and I worked pretty closely with a few customers on this recently, is like there's a million different configurations
Yes.
for tensor RT, which from the outside is kind of annoying, but once you're in there, my thought was, oh, okay, I understand why it's like this. Like, do you have any thoughts about that? Like, do you appreciate the flexibility, or is it
Yeah,
overwhelming?
absolutely. So, a great example here of what you can do with TensorRT LLM and those configurations is so when GPT OSS came out, we wanted to get some like really, really good performance on it, which we were able to do day one with TensorRT LLM. They actually published a guide, and this is something that I really appreciate about the team is they understand that it's a complicated problem. Um, so they published this guide with explanation of like all of the different settings that they recommend, which was a really strong starting place for us. They talk about like some of the trade-offs and that kind of thing. So yeah, there's kind of like two kinds of tools. There's the kind of tools that make, easy things completely painless, and then there's the kind of tools that make really hard things possible. TensorRT LLM is that second kind of tool where yeah, it's a power user tool. We don't use it for everything. We've built a ton of stuff around it to make it easier to use. We've actually built this like engine builder, and now sometimes like our sales team is deploying TensorRT LLM models into their accounts to test it out just because that configuration has we have figured out like where those smart defaults are. But yeah, it's not just enough to like pip install TensorRT LLM and your model just like gets faster. It's more that it's more that like this tool, and some of the associated stuff like Dynamo, which we're a big user of, is like the starting place, and then from there you need to have all of your configurations and all of your knowledge on top of that.
Yeah, that was my next follow-up question was going to be about Dynamo. So this is the NVIDIA Dynamo,
Yes.
not the AWS, Amazon Dynamo. Uh, how is that? Because I know that's still a roughly early, or sorry, fairly early project, but I know that team is extremely committed. But I think that didn't even really come out until GTC, right?
Yeah, so for those who don't know, like Dynamo is a distributed framework by NVIDIA. Jensen announced it in his keynote at GTC. We were actually the first company, at least as far as NVIDIA told us, to serve models with it in production a few months ago. Yeah, it's early, and we're still figuring out how to use it to its fullest potential. But a big thing that we've gotten from Dynamo is that KV cache routing, like I was talking about in one of those earlier examples. Dynamo also has great disaggregated serving support, which we're still like experimenting with a little bit to find the right configurations to get the best benefit out of that. But the KV cache routing feature has been huge for us, as has the Blackwell support, because we do a lot with B200s, and obviously supporting new architectures and squeezing all the juice out of them takes time. But NVIDIA's the furthest along there with Blackwell, of course, because it's their architecture.
Yeah. And I think the architecture that Dynamo supports, it's like very well architected. It's all like event based, and you could register for, KV cache updates and, amongst the different workers. So it seems pretty scalable. And I'm just curious, like, are there features like would you ever go back to the VLLM SG world, or you're just kind of you need the highest performance and this is all?
Absolutely. So the way we think about it is a modular inference stack that lets you swap in and out components. So we're serving customer workloads today with VLLM and with SGLang, and we'll still be doing so tomorrow. Sometimes it's just down to support matrix. For example, with TensorRT LLM, doesn't do a great job of supporting vision language models currently. The that like image decoding step is very different model to model at an architectural level. There isn't really a common architecture in the industry for that right now. So you need the flexibility of something like VLM to serve a lot of those. SG Lang, I think that team does an amazing job of day zero support for, a lot of those leading open models, especially the ones coming out of China. They have that immediate support at launch, which is huge. So definitely still use a lot of that. And yeah, the other thing is like no matter what framework you use, you can still do some of the same stuff. You can still you do your quantization, your speculative decoding, all that kind of stuff. So yeah, it's definitely a case where we just like have access to all the tools and then wanted to choose the best tool for the job.
Sure. Okay, a couple questions. Real-time inferencing for text to speech. Do you have a single batch handling multiple requests, getting to a point to understand how are we handling multiple requests in parallel for such requests?
Absolutely. So text to speech is a fun one. Let's see. So here's an example. So with text to speech, obviously you have to do all three phases. You have to do the transcription, the LLM, and then the TTS model. Looking at the TTS model specifically, you are going to be able to batch these requests. Again, like something like Orpheus TTS, it's an LLM under the hood. So um you just have the same like token level batching. We're actually serving this with TensorRT LLM. So with a variable sequence length, which is generally what you would want to use for stability in production, we're seeing like 16 concurrent requests as like up to that many on an H100 MIG. And that's got that, in-flight batching, so you're not waiting for the request for the batch to get kicked off. Every request is getting batched at the token level, which means there's no added latency from doing that batching. So yeah, you definitely are able to serve requests in parallel. That's kind of the whole point of doing dedicated deployments is, getting better cost characteristics at high traffic by serving multiple requests in parallel.
Next question, how do you deal with multi-tenant architecture, session isolation, context exhaustion, refresh?
Yeah, so there's kind of like two different products that we have, right? One is a model API product, which is more of that endpoint that you might be familiar with from like a GPT API where everyone's hitting the same thing. And the other one is the dedicated deployment where each model is on its own GPU, and traffic is routed directly to that GPU at the DNS layer, so it doesn't really interact with the control plane, doesn't interact with any other customer models. So that's the main way we deal with it, is just like pushing customers who care about those things to dedicated deployments. Obviously, with the model APIs, especially KV cache reuse is a big one there. So yeah, using Dynamo to make sure that we have as many of those requests routed to warm caches as possible is the main thing.
Got it. Okay, sweet. Let me check. There's
Yeah, Todd had a
mm,
question around, recommended places for references to lowering latencies of foundation model inference. Well, I hear there's a pretty good book coming out on this topic soon.
Todd's one of my reviewers, by the way.
Yeah.
So
Um,
yeah.
so, short of that, I mean, I try and do as much technical work on the Baseten blog around that topic as I can. I think I shared just a little bit ago one of those one of those NVIDIA things. It was in here somewhere. But NVIDIA publishes a lot, like in the TensorRT LLM documentation, in the SGLang and VLM documentation. Um, and yeah, so those are I think really great sources. And also like AI Engineer World's Fair has been publishing a lot of their videos. I did a workshop there on SGLang with one of the core maintainers of SGLang, and a lot of other people did model performance talks. So definitely check out that AI Engineer YouTube channel as well.
Yeah, let me post that link here. Yeah, they've been slowly releasing those, and yeah, I like rewatch, and I didn't get to all the talks. So yeah, that's a great conference. If you're, I think they're doing a Paris one, right? Did
Yeah,
you see that?
yeah, yeah. In like November.
Sweet.
Oh no, sorry. The Paris one's in September, and then I think there might be another one coming up in New
Oh,
York.
did they have London, I think, or something?
Yeah,
Okay.
I think New York, but yeah,
Oh,
Paris.
is it New York? Okay.
Yeah, Paris is in September. I won't be there unfortunately, but I think some of my team will be.
Sweet. Philip, man, great to see you always. I'm gonna ping you if you need to go. Yeah, that's cool. But yeah, let's get in touch after your company meetings and
Yeah.
stuff. Cool.
Thank you so much for having me. And unfortunately, I wish I could stay and talk about performance with everyone, but I have to go to a Q3 marketing on-site all team sync. So gonna go like be a real company or something.
Be a real hey man. Yeah, you have to do it at some point. So all right, bud.
Thank you so much everyone for coming out today. It's amazing to see such a huge crowd on a Monday morning.
Right on. Yeah, have a good week. Talk soon. All right, Emilio, are you ready to go, bud? Grab the
Let's do
screen share.
this.
And that's a really cool background, by the way. Where is
Oh,
that your
thanks.
actual?
It's like the no, it's like the building's like co-working space.
Oh, sweet. Oh, so it's not
Yeah.
like a fake background. It's
No,
actually a
it's
real
like
back.
a totally real.
Awesome.
Okay, let me
Yeah, don't forget
do.
to introduce yourself. Tell us what you guys do. Tell us all the fun stories we all like to hear about Y Combinator. So
Of
yeah, go ahead, man.
course. Can you see my screen just to check?
Yeah.
Okay, perfect. So yeah, thank you so much for having me. We are Herdora. We're a current Y Combinator company. We're in the current batch, and we are focusing a lot on performance of LLMs and all types of like Gen AI systems. Um, not similar to Base 10 in the way that we serve inference, but similar to Base 10 in that we build tools for companies like the one serving inference to let them profile, to let them optimize their serving, and to just have an easier way um, to just grab any model and make it run faster. Is basically the goal. So yeah, as I mentioned, we're Y Combinator back. We're currently going through the sort of Y Combinator Summer 25 batch. It's just me and my co-founder. We graduated from university and we were both doing sort of GPU engineering stuff. And we realized that it was like a great time to just go out there and try to do stuff, try to give tools to the community. We rely on a lot on like being open source. I'm going to be showcasing one of our first like open source projects. But yeah, I mean, I think I'm very excited to like hear your feedback, hear your questions, because we're just starting out. I mean, the company is 2 months old. But yeah, I'll dive right into what we've been building. So the way I'm gonna break it down is we've identified 3 problems in performance engineering, and there's probably a lot more, but the way we cluster these is first, like in an ideal world, we would all have like these optimized kernels for whatever operations we want to do. But in the real world, most people don't have access to just an engine that will give them extremely fast kernels to whatever operation they want. NVIDIA has the best kernels. They release them in like their cuBLAS and their different libraries. AMD has some good kernels now, they're catching up. But generally, if you talk to these people, these sort of forward deployed engineers at companies like Baseten, at companies like Together, or even NVIDIA, they'll tell you that it's a huge bottleneck to write fast kernels. Sometimes engineers will take a couple days or a week to write a really fast one, to write a functional kernel. But in order to write a really fast one, they'll take weeks or months of just individually working on this kernel. So that is sort of the first problem we see in the industry. The second one is how, I was talking a bit with Chris about this before, about how slow and tedious it is to profile when you want a high-level view of your entire model. Because you can either do PyTorch profiling, you can do NVIDIA Insight, you can do NVIDIA Compute, but there's no real way of just uniting these 3 views to see, okay, layer by layer, where are my flops going? But also at the same time, what is my SM utilization? So there's all these questions that you want to ask across the stack that are really hard to think about when you have all these independent tools that don't give you an overview of how your model is actually behaving under real data. And the third one, which Philip was kind of talking about in the Baseten talk, was it's really hard to know how to get the optimal inference engine parameters when you're trying to get max performance. I'm sure a lot of you have used VLLM, SGLang, tensor, TLM. These are really good inference engines out of the box, but of course everyone in this group cares a lot about performance. So that means that the out of the box will always leave up to 20% of the performance that you could get, just because you probably don't know what the optimal inference engine parameters for your specific hardware and for your specific workloads are. The optimal inference engine parameters will be different if you're doing a summarization tool, because you'll have large inputs with small outputs that you can tune at the inference engine level. That'll be very different configuration from just a sort of chatbot that normally has not that much of a stark difference between the input and the output levels as a summarization tool. So there's a lot of things you can do in this space. But yeah, the first thing I'll talk about is how hard it is to write kernels. And as I was saying, I mentioned this a bit, but it takes weeks of human engineering time. They're very error prone. It's hard to check edge cases and a bunch of other problems. The main problem is obviously this would be solved if we had millions of people who could write kernels, but this is a very sort of niche field. Even as big as AI has gotten, there are still very few people who can do it. So one interesting solution that I've seen from groups at Stanford, that I've seen from some of the companies that care the most about inference, is this sort of idea of vibe coding kernels. Obviously, the word vibe coding here might seem kind of paradoxical to a kernel, because with a kernel, you want to ensure maximum efficiency and it's like really low level. But vibe coding, I'm just seeing it as a term of giving AI the ability to do stuff with the right tools and with the right intelligence. So a recent blog post by Benjamin Anderson is sort of an account on Twitter that's like really good, and he tweets a lot about like performance. He put out this blog post about how he grabbed Claude Code in GPT-5 and was able to vibe code the backward pass kernel for GPT OSS. This was like a 2-hour effort where he just let the models, he just gave them the model the requirements. He followed a test-driven approach so that he told the models, hey, go write some tests and then test and then write a kernel and use the tests to see if it passes, and then just retry this loop. And it's an interesting article that I link here. I mean, it's very short, and like it's just a really nice view into like what's possible today out of the box. So this is sort of like the base level of just using Claude Code, maybe GPT-5 that's very new and very capable. But a lot of research groups and companies, as I was mentioning, are thinking of an approach to make vibe coding kernels a real thing, which I'm going to talk about here. So one really interesting one is simply scaling test time compute. So what does this mean? Instead of having this sort of Claude Code plus GPT-5, what you want to do is you generate with one prompt, you tell your LLM, generate an optimized kernel for this PyTorch, let's say. And then what will happen is instead of generating one, you'll generate, let's say, 100 variations. And then for each of those variations that you generated, you will check that they compile, and the ones that compile, you will profile them, and you will pass some interesting heuristics about the speed up to the original LLM, and you'll say, okay, you generated 100. Out of those 100, maybe 10 compiled, and out of those 10 that compiled, maybe 3 were faster than the baseline. So now grab those 3 and sort of recursively repeat this process of, okay, now out of those 3, optimize. So you can do this in a sort of branching out like tree-like structure where you are scaling test time compute by parallelizing and giving the LLM a lot of tokens to think about generating high-performant kernels. So there's a lot of approaches here. So this is the one that I was talking about, where you have the code, you scale based on multiple ideas. This is coming directly from the Stanford lab that's sort of like leading research on optimizing kernels with just AI. You scale out the idea, you profile the code, and then you grab the sort of surviving branches. This is very similar to if you've heard about beam search. It's simply, you can think about it as like you're putting a beam on the surviving kernels so you can continue with them. Yeah, they found super impressive results. Like they had a layer norm kernel which was a 400% speed up over the baseline PyTorch with torch.compile. So another approach that, if you know Devin, the coding agent, the company that makes Devin is called Cognition, and they also do some interesting side projects like Kevin 32B. So this is a multi-turn RL for writing really good CUDA kernels. So they will use GRPO, which basically means they'll generate sort of, let's say, 16 kernels out of one single PyTorch that they want to optimize. And then they'll have a reward function similar to what I was talking about before with the beam search, but they'll have an actual reward function that assigns a value based on does the solution compile and what is the speed up in regards to the baseline. And then you use that as signal for the model to find the optimal policy for your reinforcement learning. They saw some crazy speed ups with Quen 32B. They got a higher score in kernel bench, which is the leading benchmark for generating kernels, than Sonnet 3.7 at the time, which was the leading, and O3, I believe. And then Sakana AI is another company that does a similar approach. But what they do is they go through the LLM and they say, okay, go from PyTorch, convert it to functional PyTorch, then the functional PyTorch convert it to CUDA, but just baseline, don't try to optimize it. And then they do evolutionary search to optimize the CUDA. So they'll have the baseline CUDA, and evolutionary search will be a similar approach to this method that I was talking about before, of just scaling in parallel and only grabbing the surviving branches. So we see a lot of similarities here in sort of scaling this compute and just giving the agent or LLM more abilities to like go through sort of the conceptual space, gives them a better understanding of how to optimize these kernels. So yeah, evolutionary search is powerful. There's many ways to do it. And a lot of people are doing research on vibe coding kernels. And I think there will be a lot of progress in the next 6 months or a year. And we'll see some interesting stuff coming from here. So that's the first sort of solution. So assuming this will be advanced in the next year, we'll sort of cover that. But then the next thing that pops up is, as some of you may know, and I talked about a bit before, profiling is extremely slow and extremely tedious. Setting up the profiling takes some time, PyTorch Profiler being the easiest to set up. And then all the NVIDIA tools are really good, but are really hard to set up and have a ton of overhead. So there's no notion of having a profiler that can run in production and sort of monitor your workloads. There's no notion of being able to see the entire model layer to layer and see what is happening at sort of the individual kernel layer that could map to the PyTorch. So sort of this idea of connecting the PyTorch profiler, NVIDIA Insight, and NVIDIA Compute into one tool that is both easy to use and has very little overhead over your actual code and just gets you as quick as possible to insights. Maybe there's a ton of people that actually want to see the trace files, but I can tell you personally that most of the time, I don't want to go that deep. I just want to immediately be able to see what are the bottlenecks in my model and what should I be focusing on when I'm trying to optimize it. So how do we solve this? We published our first open source project called Keys and Caches, which you can go to the link here. And the solution that we're aiming for is a sort of weights and biases, also the play on the name, but for inference experiments. There should be an easy way to say, okay, if I enable KV caching here, what will be the result in my model? So we want to make it as easy and quick for developers to know, as I was mentioning before, exactly what are the hotspots in the model. So here I'm including an example where it's telling me that I'm running a CNN and it's telling me that the first layer is probably the only one I should really be focusing on, because that's the one that is taking up to 60% of my entire compute. And the idea with conDC is to make it as easy as possible to run. So you would pip install conDC and you would just put a decorator on top of your PyTorch. That's all you need to do. You put a decorator on top of your PyTorch that's called capture model class. And now every time you run Python, you just run Python with no extra prefixes or anything. You run Python, and this will immediately trigger, in the sort of same way as weights and biases, it'll immediately open up a web dashboard where you can analyze what is going on inside your model at all levels. So we're currently focusing on PyTorch profiling. As I said, we're like pretty new and like starting out. But the idea is to have this entire view of what's happening in your model immediately available the moment you run your model, so that you can track some experiments and you can easily iterate on what's actually going to give you more performance. So that's sort of keys and caches, and I'm sure we will talk about this more, but check out the project. The third problem that we also want to tackle, that I talked a bit about with keys and caches, is that it's very hard to tune inference engines. And Philip from Baseten was kind of talking about this, as I mentioned, but finding these optimal parameters is very difficult, and it depends on your setting. Should you use KV caching? Should you use spec decoding? If so, which implementation? How do you get to the max GPU utilization possible while not seeing those horrible CUDA out of memory errors? What about chunk prefill? Everybody's talking about that. All the cool kids are talking about chunk prefill, quantization. What should I quantize to without losing accuracy? There's so many questions that an LLM or that an LLM engineer has these days. And it's just a massive permutation problem. It really is. It's like flags that you can either activate or inactivate, and an array of numbers, which you can take as discrete to sort of say GPU utilization, and then just permute and then see what will give you the optimal inference given the workloads that you'll be receiving. So this is what we're currently working on and like really trying to get out there for the community and just make it completely open source, because a lot of people from what we talked to at like the big companies like Together, like Baseten, have these tools internally, but the community doesn't really have these tools. There's no real way to just say, sweep through my model.py and find the optimal parameters. And we think that should exist. So it's basically this, an easy way to find the optimal parameters. It'll depend on the specific hardware you're on, because that'll define a lot of the things of what specific parameters we should use. It's not hardware agnostic. It depends, like if you should be using sort of KV caching, depends on what hardware you are, what your GPU utilization is. There's a lot of parameters that you can optimize. But yeah, as I mentioned, it's fundamentally a parameter permutation problem. So if I could personally just define my model in my GPU, set up VLLM, and then just run a sweep that finds the optimal parameters that'll run VLLM immediately as fast as VLLM possibly could, then I would be very happy with that. And that's something that we would want to see in the open source community. But yeah, that's basically the three problems we're tackling. And I'll go back to these just to remind: writing fast kernels is hard, profiling is slow, and it's hard to know the optimal inference engine parameters. We're just starting out. Our project is keys and caches. The easy link is condc.ai. But yeah, thank you so much.
Yeah, man, looks great. And you folks do have like a little video teaser and things right off of Conc.
We do.
Okay.
Let me find that for you.
So we got a bunch of questions, which I was hoping for, and it's very similar questions to what I was going to ask anyway. So let me just go through them. Oh, actually, a high level question is, with all of these like Berkeley or Stanford projects and things that are happening with the evolutionary, how are you working with those teams? Are you just like reading their papers and implementing it? Or the Bay Area is very different than the rest of the world. So
yeah, I think that's one of the most surprising things from the Bay Area, actually, you mentioned, Chris. It's just like everybody is willing to collaborate. Like I read some of these papers, and I read Anne's paper, which is actually a blog post, because they were just, as they said, they were like surprised that they found good results so fast. And I like reached out on Twitter and just like talked about it. And also Benjamin, like I just reached out on Twitter and we just talked about his ideas. So it's been that's sort of like what collaboration means to me right now. Of just like, can I reach out to them on Twitter and talk about their project? And that's been like extremely good. No official collaboration, but hoping that something like that gets in the moving.
yeah, and it's interesting because I think there's probably folks on. I've been getting pinged here on the side, like, how, like, aren't you worried that these three or four Stanford folks aren't going to go off and create a company? Things like that, right?
Yeah, they should. They should definitely create a company. I mean, it seems. I mean, I think our goal is very much so like, we are open source. If someone is going to go and create a company that's open source and do it better than us, then that's just like natural selection. That's like what the community has chosen, and they probably should win. But like we just want to like we just want to add stuff to the community, and then think about like, yeah, at some point we're going to have to think about business. But for now, we're just like two 22-year-olds that really care about performance and want to like put stuff into the world and see what happens.
For sure. And I think the first time you and I connected, I was like, doesn't Y Combinator make you have to have a product? And your response was very honest and very genuine. Yeah, I mean, do you want to repeat it or just kind of share that?
I mean, I think the most genuine answer that I can give is, I mean, yeah, what actually happens, which is we put out these projects and then companies just reach out to us and are like, hey, I saw your project. I'm having trouble with like, I have these problems. Like, can you guys help with your tool? And most of the time, with our current state of the tool, we probably can't. But a lot of the time, it's like we can probably build you a solution that's very personalized to what you want. So I think we really like this structure where open source just gives us a way to add a bunch to the community and collaborate with the community, while the companies that need to productionize services that we offer still sort of need to talk to us, because operating anything at the enterprise level needs some features that they need, as you've seen with like other open source tools, like collaboration features with teams, like storing data for longer, like SLAs, like all these like business things that are more boring than the actual product. But like we still think there's space for like making money and balancing that with just like publishing tools for the community.
Yeah. And right, because my understanding of Y Combinator was that they are on you every week to, talk to like X number of customers, get the
Yeah,
feedback. So you're going through this process, and you're talking to hundreds of, potential customers or just users of,
yeah.
people that, and I guess what you're doing is putting out open source, like generating the buzz, showing, you're sort of in an educational phase, I guess, right?
Yeah,
And
we're
okay,
very, yeah, we, as exactly you say, Chris, like Y Combinator will, like the one thing that sort of buzzes in my mind all day after this weeks of like Y Combinator is talk to people, just talk to customers. You think you know what people want, but then you actually do the thing and you give it to
yeah,
people, and they're like so confused. They're like, okay, this is, they don't think it's the right way. There's like a million things going through everyone's mind. So I'm like talking to people all day. My co-founder,
yeah,
my co-founder like actually writes most of the code these days, and I just talk to people and just like hear about their problems when trying to optimize things. It's just like
yeah.
not even trying to prescribe something to them, just sort of like, hey, like what's the hardest part of your job, and just seeing where we can add something.
Got it. And what's cool about that is the people you are talking to don't feel pressured to be, paying for anything. They're like typically happy to help you, you know.
Exactly. Yeah.
Yeah. And you're certainly very mature for, 22. Um, yeah, like amazing that you sort of found this space. I think it is a real problem. What's really cool about this space, and I think you and I spoke about this on the phone the other day or on Zoom the other day, was there's a clear value prop to this, right? There's 400%, 484% performance, gains and
Hmm.
things, and I mean this is just amazing. And with the scarcity of GPUs and the high cost and things
Yes.
like that. Um, One thing, so you mentioned weights and biases, which I picked up on when I saw keys and caches. I thought that was pretty funny.
Yeah.
Yeah, that's cool. Um, Weights and biases classically has been considered sort of like just storing data and visualizing data, the
Mhm.
experimentation data. I know that they have that product called Weave that does some kind of agent thing. I actually don't know much about it, and now they're actually part of Core Weave. Um, they were recently acquired, but you folks are doing more than, or plan to do more than just collecting and profiling and showing. There is
Yes.
a clear like optimization step, right?
I think there is a clear, and this actually goes back to what I was mentioning of these companies reaching out and telling us about their problems after our open source projects. They tell us that they have this similar workflow of, okay, I have a sort of program that I want to run. I have the LLM that I've chosen that I want to run. I have a bunch of options of what I need to choose. I don't want to go to these providers that just give me an API because I want control of my own stack. But also my engineers don't know how to like should they choose VLLM? Should they choose SGLang? Once
Yeah,
they choose those, 200 other questions open up that I was talking
yeah,
about like what exact parameters should they use. So what we're seeing the most and what we've been building for enterprise in a sort of very ad hoc and bespoke way is a sort of co-pilot for optimizing your inference. So you'll tell it the requirements, you'll tell it what you need, and it'll go evaluate and easily experiment. So you'll say, okay, if I add KV caching, would that give me a speed up over the data that I normally get on this specific model? And it would have access to this data, and it would analyze the specific, like what's the input output ratios. It would analyze specific data that tells it, okay, let me go and run experiments on what will be the fastest. So this is
mhm,
why I was describing this to you like earlier, as like the Devin for like performance of just like automatically going and like trying things and seeing if there are speed ups. So I think it's going on a more, just because of like how powerful AI now, it's going on a much more agentic direction than what you mentioned of like weights and biases, which is like probably they were probably found in like 2010s or something. It's like
mhm.
at that point there was no capabilities to just even think of like a system that could automatically do the job of a performance engineer, at least a very narrow subset of it, because it's still a very broad and complicated field. But now there is some notion of like you could run experiments without any human in the loop and just give you the results of like, okay, here's a performance speedup that I found from KV caching. Should we implement it in prod? So it's like a very interesting space right now because there might be some options for automation.
I was talking to a big like enterprise customer the other day, and I realized that they're not alone in the, they've tried SGLang, they've tried VLLM, they've tried TensorRT, and every time that they switch engines, they have to relearn all the configuration parameters, all the, where are the gotchas, the, different KV cache implementation, spec decoding, support. And they're just in this sort of analysis paralysis type phase,
Mm-hmm.
right? And
Mm-hmm.
they're not ever getting super deep into one. And then they hear about a new feature and another one, they want to go try that. So any tips for folks on what to do there?
Yeah, I think okay, so have you seen Modal's sort of guide to
Yeah.
yeah,
Yeah.
that one's really good and it's the one I always point people to. It's sort of not trying to
Yeah.
like
Charles.
yeah,
He
Charles Fry is
presented it
amazing.
recently.
Oh, really?
Yeah.
He was showing
Yeah.
it?
I think we had him on actually last month.
Yeah.
It's called the LLM Engineer Almanac or
Yeah, okay,
something.
I'll send it anyway. But yeah, Charles is amazing. Great presenter. And okay, there we go.
Yeah.
And it sort of runs you through like what are your requirements and what inference engine should you be using and what hardware are you running on. So all these variables. But I think generally um, the advice that like what we follow internally is just be very strict about defining your baseline and defining your current performance, and then just have a loop where you take a lot of notes of where your performance is currently at and then run a lot of experiments on top of that. But then always like I think the biggest pain point for us was sort of okay, we've ran this parameter, we've ran like KV cache enabled, but there's this other variable that we also changed. So like now we have two variables and we don't know which one is which. So just like I think the general tip is just like be very like scientific of just like change one variable and see what happens. Don't try to do multiple things at once. Even if you type it into ChatGPT and it's like, oh, you should enable
Right.
prefix chunking, you should do KV caching, and then you do it all at once and you're like, okay, now it's at 0.6% of the speed up. So it's like, what happened? It's impossible to
Yeah.
know if you're doing a bunch of things at once. But yeah, there we go. This is an awesome
Um,
resource.
yeah. And when he spoke at the World's Fair a few months ago, he said something interesting, which was they found that so the engines that they support here are TensorRT, LLM, VLM, SGLang, and I think there's an open source project that provides all the configurations and the Docker images and things. The one big asterisk here is these are just sort of default configurations. Like
Mm,
I feel like there's another dialogue drop down that should be added here, which is like, all the 10 million different configurations that TensorRT LLM has. And,
totally.
so he's kind of doing a little bit of a apples to oranges comparison maybe or something, but it's a good baseline to like understand, okay, here's some like characteristics that I'm looking for. I'm trying to achieve the lowest latency or highest throughput. And
That would be
so
super useful. A version of this that just shows you like the actual drop down of all the flags and parameters you can enable
and
for
the
each
and
one.
the combinations and lets you run it sort of in like real time on the different GPUs because it looks like this is actually hard coded for H100. And oh
Mm.
yeah, that was something else I was going to ask you. So I when I watched your teaser video for keys and caches, I noticed that you actually support running it on different GPUs. Is that right?
Oh yeah, we love all. Let me show you. We
That's
love
a cool
alternative
feature.
GPUs. Yeah.
Yeah,
I'll
man.
actually show you. I'm actually going to show you an interesting thing that we have called chip benchmark. We care a lot about performance on different hardware. So this is Llama 3.1 AB. Let's just use this for example, and then we can use let's say yeah A100. So here is like our top choices normally for running models, but we also really care about like AMD because we think there's a lot of cool stuff that they could do in terms of like they could really take a percent of the market, and they are in track to take a percent of the market, at least in the next 5 to 10 years. So that seems like a really exciting place to be, because if you see like the graphs and you go to perf per dollar, you'll see that the MI300 is already giving you more performance for every dollar you're paying, simply basing it off of like the price that MI300Xs are available right now on clouds. So that you can go to this repo to see like where we got the actual pricing. It's all open source again. But like this is not exactly what you were mentioning, Chris, of like the keys and caches, seeing on different hardware. We do support H100, A100, L4s, everything from NVIDIA. We're working on supporting MI300, but we also think a lot about just benchmarks and seeing like what actually runs fast depending on the model and depending on the hardware. Yeah.
Cool. Good stuff. And so I can envision like your service, and I've been thinking about this myself also, just sort of mentally, is like take the same workload, upload it to your API, or use your open source project, and then have it launch on the different clouds, do all the different profiling, do some self-tuning, things like that, and then produce the best combination, right?
Exactly. And just let you serve it. We're not going to ask you that now that we produce the best combination, you can only serve it on our cloud. It's just for you. Take it wherever you want.
Got it. Okay. I do want to get to a couple quick questions, and then I'm going to show real quick my demo as well too. So let's see. I think someone was asking about correctness. So do you want to address that?
Correctness in like when you're quantizing, seeing that it's still accurate.
Yeah, exactly.
Yeah, that's a big one. And we're actually so we were thinking for this customer who really wants benchmarks, just like evals. We started running this like agent that you can give the sort of benchmark that you want to run, the data set, and it goes and checks accuracy at different quantizations. So currently we'll be super conservative. Like we'll let you choose we'll let you choose up to like FP8, whatever you want to use. But it will mostly be up to you to check accuracy. So we have no solution for you to tell you, okay, we tried the permutation space and we went to FP8, but we lost accuracy. The idea is that we just give you the model on FP8, and it's super easy for you to go and run it against your benchmark that you already have. It is a very interesting direction. But for now, we're very focused on just like performance, and it's very important to take into consideration that some of these performance tricks might degrade actual like correctness. So it's something we're thinking about, but I can't show much on that regard yet. We'll have an update in the next week or so.
Okay, cool. Sakana, the famous Sakana. So someone picked up on this. They were famous for announcing that they had a faster kernel, and then they ended up like retracting it, right? Because like RL chose to like reward hack, and ended up. So but there's also, I think Predabase also did something that was like RL based, the company Predabase, where they were able to generate a faster kernel, and NVIDIA themselves has a loop. I actually like talk about all this in the book. That's how it's on the top of my head. But
nice.
So has Sakana actually like recovered from that? Like, meaning, have they actually gotten something to work like after that?
They did. This is, a lot of people tell me this. It's kind of sad because it's such a great research lab. And they had this one mistake, and it was like a Twitter account. Like a Twitter account, like a pseudonymous Twitter account, this like cracked person was just like, hey, your agent is reward hacking. Like this is not true. And they like pushed it back, but a couple weeks later they released the new version of the AI CUDA engineer with that fixed, and they didn't see the same speed ups as the first one. I don't have the actual numbers off the top of my head, but they did release it with the actual patch of just like the reward hacking. This is actually exactly the same problem that Kevin 32B, the other RL method I showed, had, where the agent would just like, instead of writing the CUDA, it would just do like torch.compile, and then there would be a speed up, and it'd be like, great. So there's a lot of reward hacking when you're doing reinforcement learning, and I think Sakana recovered from it a bit. But yeah, I guess it's still, people still remember it by the reward hacking people.
Is Kevin 32B, that's from Cognition?
Yes, it was
Got
actually
it.
an intern project, which is super impressive.
Oh, funny. Right on.
Yeah.
Okay. Okay, yeah, Kevin 32B, got it. Okay. So I might actually add this to the book because this came out
This is
since I wrote.
it's quite a good paper. They explain it really nicely. Wish it was open source, but you know, and the model weights are open source, but you also it's hard to run. GRPO is just so expensive. But yeah,
Yeah. Okay, and I think there was another question I wanted to get to, and I lost my questions here. Sakana. Oh, and then okay. Oh, yeah, someone asked about performance counters, and so those are coming from NSYS and
yeah.
NCU, right?
That's actually like a tougher problem that you would think of initially, just because most providers, for security reasons, can't give you access to hardware counters.
Yeah, yeah,
Did we talk about this, Chris, when we first met up? Just like how like RunPod, I love RunPod, by the way, they're great guys, but they won't give me access to hardware counters.
yeah.
Modal, oh, I don't know if Modal does. Do you know, Chris?
I meant, and you and I have not spoken about this.
Uh-huh.
I keep forgetting to talk to you about this, but I actually don't know. We need to ask Charles.
Yeah.
I don't imagine that they do, but so the short of it here is any cloud provider that you use, like typically doesn't give you access to the counters and like the really low level information that's needed for like the insight systems and the insight compute,
Yes.
and even perf counters. I don't think even just regular
They
CPU
don't. They
counters.
don't.
Yeah,
It's very annoying. Yeah.
and
We actually have to
so
just like talk to them like this is where like Y Combinator helps in, because we just like talk to our partners and they know people at like these cloud companies, and we just have to ask for like special permission to like add to like because we don't have GPUs. Like it's not like we can just go to like our H100
yeah,
cluster in our basement. There's no
yeah,
solution for us apart from like just like stop working.
yeah. And even, I mean, even like, I think, I'm having problems getting counters even with some of the Neo clouds as well, too.
Oh yeah.
Um, so the solution, of course, is just to try to provision bare metal.
Uh-huh.
But even in, some of those cases, yeah, they prevent you. So the short of it is it's very difficult to get this type of performance information and, the ability to like profile at the level that you need if you don't have your own servers somewhere sitting. Yeah. Um,
Exactly. Exactly.
maybe Oracle Cloud, maybe,
Oh,
but
maybe. I haven't tried them. I hear they're
yeah,
growing a lot, but yeah.
yeah, I'm seeing Oracle Cloud popping up everywhere. In fact, when I was
Yeah.
back at AWS, we were always evaluating, like comparing our infrastructure to theirs and things. They have a really fast network. They're all InfiniBand. They fully buy into the NVIDIA reference architecture and things like that.
Mm.
So yeah, a lot of customers really liked them. Okay. Was there a link to the repo with chip benchmark?
Oh
What is
yeah,
that?
of course. I'll send it. Don't worry, Chris.
Okay. Yeah, the video will be posted. Actually, let me quickly show, where is my demo
Super
here?
excited to see your demo, by the way.
Yeah, me too, because I just got it working like a couple
Nice.
hours ago.
Okay.
Okay, so, and it's going to be right now, it's kind of almost where you folks are, but slightly different UI or whatever. But the idea here is you could right now just choose a simple .py file. This is just to get something going. We'll select a naive attention. You could pass in any custom arguments. Give it the number of variants. The key here is you want to give warm-up steps, the number of iterations to actually let your PyTorch code warm up. That way, if you're doing torch compile it and it'll allocate everything before you start measuring. Then you would click start. It starts going here. Why I was really excited about this particular coding effort was I'm not a UI person at all, and so I was really relying on GPT-5 and Claude to help vibe code here. But so it kind of shows the baseline code. It's going to show some variants. So let me actually just jump over to one that's already working and that I've already run. So this one, I think it's the exact same code. And we've got the leaderboard up here. So the different variants, all these variants right now are being generated by one of the GPTs, in this case Claude. I think I'm using Claude 3.7 just because it's a little bit cheaper. Some of these actually fail, and I'm sure you've noticed this, some of these versions. And so I've got a hotfix path in here as well too, where you can kind of go in and say hotfix, or do an auto hotfix where it'll go back to the GPT, show the error in the source code that was generated, and then regenerate it and add it as another variant. But yeah, here we could see top operations. You see I'm not getting the CUDA timings that I was hoping for, but I am getting some of the CPU timings, so that's a step forward. And what's really cool is I can generate this report that I pass in the environment. This is a GH200, so Grace Hopper 200. Got a lot of system RAM, a little bit of GPU RAM, and it can go through and actually analyze. And of course, all this is just coming right back from the GPT. So right now, there's no RL in here. There's no like evolutionary. There's no, yeah, like no beam search or anything like that, but it's kind of a stepping stone. So this is what I want to talk to you about, because this is sort of similar to the keys and caches, and I would love to collaborate and
This is
do a little bit
awesome.
more.
Wait,
Yeah.
can you talk more about how it knows how to optimize in the background?
Yeah, it's and there's really nothing fancy here. This is purely just a, yeah, just a Claude wrapper, basically, right? But the the trick is to feed in as much of the profiling info. So the very first thing
Mm.
it does is it just tries to run the baseline, tries to get this thing going, and it's sort of learning as it's go. Oh, yeah, the other thing I didn't mention is I'm actually doing RAG on my own book. And so that was the other trick, was
Mm.
there's almost there's no one place that has all of the information that my book has, which is why I was writing the book. And so I'm actually performing RAG um, based on this code. I do like an initial pass to describe what the code is doing, what are some of the possible um, improvements, right, that I could do for performance. That I'm going out to the book, I'm pulling in relevant excerpts, I'm passing all of this information, the environment, as well as the code, as well as the RAG excerpts from the book, pulling it in, passing it to the GPT, asking it to then generate different variations. But the really cool thing is it sort of explains to you what's going on. So it's not just generating the variants, but it's sort of helping you understand. So I was trying to make this more of an educational spin also, so it's going to optimize, but it's also going to teach you, like, why is this actually happening? So, here's the approach that's being taken, and the expected effects, which ones worked, which ones didn't. Let's see, this one doesn't have the detailed report. Let me grab that one. Grab an
Well, I love
example.
that it did RAG over your book. You need to give us an API service that just a RAG over
Totally,
your
yeah,
book.
yeah. I'll just give you the book. Yeah, it's not a big deal.
That
But
actually works best.
this is the deep explanation. I mean, the other thing, of course, is to just do like a web search and sort of simulate all that and pull in all the like relevant material. What I noticed writing the book is, there's not that much material on this stuff, right? And I mean, there's barely enough on like Hopper. There's almost nothing on Blackwell. Like, I think we've probably talked to most of the people that are even doing Blackwell performance tuning, right, outside of NVIDIA anyway. Yeah, we probably know all those folks. But this is the cool thing here, is this deep explanation. And right now it's just a markdown that has that takes into account all this information. And then what I want to get to is to the point where I could actually pull these out and put them up to the variants and, really inline explain, but it's explaining to you which variants worked, why did variant one outperform variant two, talks a lot about tensor core optimizations, even does like my favorite here, which is ASCII art, showing, how these different visualizations work. So at some point, this will actually pull in the diagrams from the book and, explain things or pull things from the web. But the reason I went with the book was because it's one resource that has all of like the relevant, aspects here, like versus going out and doing 10 different web searches and having some stuff. I mean, there's stuff out there that's just wrong, right? Wrong number of like SMs, wrong number of, all different aspects. But yeah, this is really cool. And once you start passing in some of the more advanced kernels, it starts to get like really sophisticated and starts talking about, well, you should be using thread block clusters here and here, and so some of the newer features of Blackwell and tensor memory accelerator and things like that. But yeah, this is just a basic fuse, fusing and then quantizing and using, yeah, like you were saying, yeah, just turn on torch compile and that should like take care of everything. But at some point, I was testing this weekend about generating pure CUDA kernels and comparing performance, and I made a little bit of success. The other thing was I started actually generating pure PTX. So just basically bypassing, all of this, like, yeah, not even like generating Triton, not even generating, more like PyTorch code or CUDA kernels, but just generating PTX. It's not good at that at all, right? I mean, because you need thousands of lines of PTX, which these GPT models aren't doing very well at right now. One final note on this is there was a really good podcast with that Greg Brockman guy, one of the co-founders of like OpenAI this weekend, or that I had listened to this weekend, that was on Swix's Latent Space podcast, where he's hinting that the newer generations, I guess it would be GPT-6, are starting to get really good at generating CUDA kernels. And
Really?
so, yeah, it was one comment that he made. Swix didn't really pick up on it, or or he had picked up on it, but he didn't dive into it afterward, after Brockman said that. But yeah, Brockman said, just like you said, within the next 6 to 12 months, they will be at a point where they can almost auto-generate, these kernels, and improve performance. So yeah, like keep an eye out for that. If you can, try to get a hold of those guys over at like OpenAI and see if they're doing
Yeah.
anything with that.
Yeah.
Yeah, use your connections, but
Well, that makes sense. Wait,
yeah,
it feels these optimizations feel way more targeted and sort of a knowledgeable LLM than the ones you just get out of the box for Claude Code. And normally, when I just try with Claude Code, it's probably because of the RAG on your book and all the tricks you did. Normally, when I
yeah,
just try with Claude Code without any context, it just does not know like
yep.
how to approach optimizing things generally.
Yeah.